Hello, everybody. Welcome to the AutoChem webinar. This is the first webinar after the summer vacations, so I hope you had relaxing vacations this summer. It is my pleasure to introduce today Olga Smirnova. It's really a privilege to have her in this webinar series. Let me say a few words about her for those who do not know her. So Olga got a degree in physics and her PhD at Moscow State University. And then she moved as a postdoctoral researcher to the Technical University of Vienna, where she spent a few years. And then she moved to Ottawa, where she spent also a number of years before she came to Europe, in particular to the Max More Institute, where she is working today, and she has her own group. She's also a full professor at the Technical University of Berlin, and her research work has been mainly focused on attosecond science, almost from the very beginning, and she's one of the big names in this area, in the theory of attosecond science. And in particular, in the last few years, she has developed theoretical methods, and she has proposed very interesting ideas to study chirality in molecules by using attosecond light sources. And this is precisely the topic of her talk today. She has received already several awards, but let me just highlight the very last one she got, which is the Ahmed Sebael Award in Ultrafast Science and Technology, awarded by the American Chemical Society, which is an extremely prestigious award. So I don't want to take more of your time, so I repeat, for me it's a great pleasure to have Olga today here. And I'm sure that you will enjoy her seminar. So please, Olga, whenever you are ready, you can open your camera and share your screen. And
thank you.
Sorry, I forgot, very important point. If you have questions or comments after Olga's talk, please go to the platform, to the Q&A panel and write your question. And I will read them after her talk, and I will ask the questions to her. Thank you.
Thank you very much for the invitation and also for the introduction. I'm very honored and very happy to speak to all of you today and present our very recent results on ultrafast chirality. Let me first share the screen with my presentation, and then we can start. I hope you can see my screen.
Yes, we can.
Thank you. So I will talk about ultrafast chirality, twisting light to twist electrons. You all probably know what chiral objects are. They are just like my left and right hands, two non-superimposable mirror images of each other. Non-superimposable means that no matter how I rotate my left hand, it will never look like my right hand. So molecules can also be chiral, and it's difficult to distinguish left and right molecules. So before I tell you my story today, I would like to thank my co-authors and people who contributed to this work. My excellent PhD student, Andres Ardanes, who completed his PhD and left us, and he is now in Barcelona in IGFO. David Ayuso, my brilliant postdoc, now moved to Imperial College London. Both got very prestigious fellowships, and I'm very happy for them. I would like to thank also Piera Dekleva for the collaboration and Misha Ivanov. So I will tell you today two vignettes which illustrate and support the statement that nonlinear light-matter interaction leads to new, extremely efficient chiral observables which work already in the electric dipole approximation. So my first vignettes will be about twisting electrons. And I will tell you about geometric magnetism in photoionization of chiral molecules and new enantiosensitive observables in nonlinear photoionization. And the second part is twisting light. I will speak about synthetic chiral light. This is the light that we have introduced, and it is chiral in electric dipole approximation. I will introduce the concept of chiral Young's double slit experiment and also, of course, new enantiosensitive observables in nonlinear optical response that arise in this situation. So I start with the first vignette, and I would like to formulate a question which I find interesting. We know that in solids, nuclear configuration or lattice determines fundamental geometrical properties such as Berry curvature, topology, and anomalous observables stemming from Berry curvature, such as the Hall current. The question that I would like to ask is the following. Are there geometry-induced anomalous phenomena in molecules? And is there a common source of these phenomena, such as a geometric field? So indeed, chiral molecules have an additional purely geometric degree of freedom, and this is handedness. And you can see there are two molecules of propylene oxide, left-handed and right-handed form. And stereo arrangements of the nuclei of these molecules define potentials in which electrons move. So in a sense, they define tracks for the electrons. Electrons moving along these tracks, which may have very complicated topology or geometry, they generate currents and fields encode the geometry of tracks. So this is a very naive idea which allows you to see how the geometrical degree of freedom maps into ultrafast response currents, electron currents, and geometric fields that these currents generate. And what you will learn from my talk today is that this naive perspective is actually not so wrong. And the answer to my question, are there geometry-induced anomalous phenomena in molecules, is positive, and is there a common source of this phenomena, such as geometric field, is also positive. And the answer is yes, these all exist in chiral molecules. Some of these effects are known but not recognized as such, and some have never been looked at, but I find them spectacular, and I will talk about them today. So in this part of my talk, I will be dealing with photoionization. The most important and remarkable effect in photoionization of chiral molecules is photoelectron circular dichroism. It occurs if we apply circularly polarized field and photoionize the molecule, and electron has the final state with the momentum k. So if we apply this circularly polarized pulse to randomly oriented ensemble of, say, right molecules, and place two detectors for electrons along the propagation vector of the ionizing field, then we find that more electrons will go into the, for example, forward detector than into the backward detector. It means that there is a net photoelectron current. And this current changes its direction if we change right-handed molecules to left-handed molecules, which means that this current is enantiosensitive. And the sign of this forward-backward asymmetry, or the sign of this photoelectron current, defines distinguishes left and right enantiomers. What is extremely important that the enantiosensitive signal is huge. It's of the order of the total signal. And that what makes PECD an extremely efficient proof of molecular chirality. What I have told you so far are well-known things. What is new, and I will tell you about it today, is that PECD is a manifestation of geometrical magnetism, and PECD is generated by the flux of the geometric field. And this is not the only news. Most remarkably is that PECD is only a tip of the iceberg, and the iceberg is the geometric field and phenomena that it generates. And this iceberg also includes new classes of enantio-sensitive observables. So the PECD current can be written in this form via conductivity. Conductivity and the electric fields, electromagnetic fields, that circularly polarized field that generates this current. Interesting, conductivity can be written as a flux of a certain field through the sphere, which is simply the energy shell for the electron, which means that this sphere is in the momentum space of the photoelectron, and its radius is absolute value of k, which is given by square root of 2 electron energies. So the flux of the field through this sphere defines the conductivity and defines the strength of an enantio-sensitive response. So forward-backward asymmetry is generated by the flux of field B, and this B field is defined as a vector product of photoionization dipole and its complex conjugate. The photoionization dipole is a dipole which connects the ground state and continuum state with the momentum K, with the final state which is characterized by the electron momentum K. So this field is an independent of light properties. It's defined in the molecular frame and it's unique to a molecule. Its flux quantifies the chiral response in PECD. Well, it turns out that this is a geometrical field, and to bring this concept to this talk, I would like to compare interband excitation in solids and photoionization of molecules. And the basis for this comparison are these pictures that you see here, which allow us to relate these two phenomena. So what you see on the right-hand side are two surfaces in K space, in the momentum space. The lower surface is a band, which is, for example, valence band, and the upper surface is a conduction band, and the arrow indicates the transition, which places the electron from valence band into the conduction band, and this transition is initiated by circularly polarized field. On the left, you see a similar picture which reflects photoionization of molecules. It is also represented by surfaces in K space, in the momentum space, and that is why the lower surface is degenerate, and because the ground state does not depend on K, and the upper surfaces is parabolic. It quantifies the molecular continuum. Now, the geometric field and molecular photoionization that I have just introduced can be also rewritten in this form, and the difference between this and this form are just different gauges. This is the length gauge, and this is velocity gauge. And the Berry curvature in a two-band solid can be written in a very similar way. You see that these expressions are virtually identical. Here we deal with the photoionization matrix element, and here we deal with the transition matrix element connecting these two bands. So the objects, this and this, obviously look very similar, and both have geometrical nature. What does it mean, geometrical nature? It means that they reflect curly, twisted electron polarizations or curly twisted electron currents. And the parallels between these two objects run deep. For example, there is a phenomenon which stems from the Berry curvature, and this is a circular photogalvanic effect. And this phenomena is strikingly similar to PECD. It occurs in chiral solids, or in solids with broken inversion symmetry. And the essence of the effect that you apply the circularly polarized field, and it promotes electron conduction band, and the net current arises, which is directed along the propagation vector of the field, which used to inject the electrons. And this current can be written in the following form, where sigma is a conductivity, and conductivity is given by the flux of the Berry curvature through the surface of the Brillouin zone. And you see that this conductivity, which is a flux of Berry curvature, and that conductivity, which is a flux of geometrical field in molecules, are very similar in the way how they are connected to conductivity. So now the geometric field in molecules can be related to purely electronic structure. And this is what happens if we start photoionization from a single stationary state, for example, ground state. And this is what happens in one photoionization, and this field emerges due to purely electronic structure. And if you look at this field, and this is what we plotted, so the sphere is this energy shell for a given photoelectron momentum. Each arrow shows the direction of the field for a given k, for the given vector, because the sphere, the radius vector of the sphere defines the direction of photoelectron momentum. So you see that for every photoelectron momentum, we have certain field. It has a direction and the absolute value given by the size of the arrow and also color. So red is most strong field, and blue is small field, and here it has a 0. So in this case, the property of this field is such that only radial component of this field integrates to a non-zero value. And this is what is flux by definition. So the flux which quantifies PECD. But we could imagine a different setup in which we first excite dynamics in the molecule, for example, using linearly polarized pump pulse. What happens in this case is that chiral currents evolve, and they can be later probed by the probe pulse. So the chiral currents evolve, and what also evolves is a component of the geometric field, which is related to dynamics. And after the delay, we can probe it with circular probe. In this case, geometric field generated by ultrafast twisted electronic or vibronic currents. And dynamics offers additional control over the geometric field and phenomena it induces. So what you see in this case is that we look at the geometric field generated by currents. And the simplest possible case is when we excite two states in the molecule, and the energy difference between them is shown here. And in this case, the geometric field encodes the coherence between the states, and it involves photoionization dipoles from each of these states. So in this pump probe setup, the field emerges both from the curly electronic structure or from twisted currents. And thanks to currents, not only the radial component of the field, but also the whole field integrates to a non-zero value. And this leads to a new class of enantio-sensitive phenomena. So a geometric field generated by the dynamics at this frequency can be represented in a form which exposes its symmetries in the most clear way. So for that, it is useful to introduce field quadratures. Q quadrature characterizes rotational asymmetry of electron density. This is what I was saying chiral polarization. And P quadrature characterizes rotational asymmetry due to electron currents. And this is what I previously called twisted currents. So these are two origins of the field. And also symmetries plus and minus, these are symmetric and antisymmetric combinations of this field in left and right molecules, and also symmetric and asymmetric antisymmetric combination with respect to K to minus K change. So now what we are in fact interested in, because this field is defined in molecular frame, we are actually interested in quantities which are global invariants of this field. So the quantities which result from integral over all orientations of vector K, all directions of vector K. And this is the first global invariant if we just take field and average it over all directions of vector K. And in this case, we trace out photoelectron. And it means that first global invariant will characterize the molecular core. So based on the symmetries of these components, one can show that only one component leads to global invariant, and it arises due to currents. And it presents new, it corresponds, and it can induce new enantio-sensitive, dynamical enantio-sensitive observables. What I would like to mention is that both the geometric field and its global invariant have been overlooked until now. So these are really new objects. And the new observable, one of the new observables that they correspond to is molecular orientation circular dichroism. So the new effect is an enantio-sensitive orientation by ionization. And in this setup, to induce this molecular orientation circular dichroism, we need the following setup in which we use the linearly polarized pump, and then with delay, circularly polarized probe comes. I would like to note that the exactly same pump probe setup was used in time-dependent PECD, and the angular distributions of electrons were recorded to obtain PECD observable. And in this case, what one needs to look at is angular distribution of fragments, not electrons. Now, what is the physics underlying this phenomenon, enantio-sensitive orientation by ionization? So consider two right enantiomers of propylene oxide, which are oriented oppositely. So, and what happens is that after they are excited, there will be a current excited in each of these molecules. But the current will have different geometry. The thing is that molecular field is a property of the molecule. It's defined in the molecular frame, and it has the same orientation in the molecular frame. But for these two molecules, it has opposite orientation in the lab frame. And the current due to which this field emerges, for that reason, rotates in opposite direction in this enantiomer and in that enantiomer. And the molecule in which twisted current is co-rotating with the probe field will be preferred for ionization due to well-known propensity rules. And therefore, there will be more fragments like this than fragments like that, because this ionization of these molecules will be suppressed. So linearly polarized pulse excited bound electron current and the geometric field, molecules where this geometric field is oriented along the propagation axis of the circular probe will be preferentially ionized. Now, our preliminary results shows the what is quantitatively how large these orientations. First of all, the interest to this photoionization enantiosensitive observables is dictated by the fact that they are working in the electric dipole approximation, which means that they should be really significant. So our preliminary results for propylene oxide shows that average angle between the unit vector characterizing the direction of orientation and z-axis characterizes the lab system, the direction of propagation of the ionizing pulse. The cosine of this angle can reach 0.12. So what does it mean in simple figures? It means that out of 100 ions produced, 60 will have this vector in the lower hemisphere and 40 in the upper hemisphere. This is a very significant orientation, and we expect this effect to be significant, although these are preliminary results which we obtained for LUMO and LUMO +1 excited states in propylene oxide. I'm moving more towards conclusion and generalizing this vignette, and as a very exciting outlook, I would like to say that the geometric field allows us to classify enantiosensitive observable in photoionizations. And these enantiosensitive observables can be classified as simply global invariants of the field. So the first global invariant of the field, and this is what I discussed today, this is molecular orientation circle. The first global invariance is the net geometric field, the field which obtains if you average over all orientations of vector k. This field leads to vectorial observables of the cation, and molecular orientation circle dichroism is one of them. The second class of observables are chiral observables that rely on the second global invariant, which is a radial component, total radial component of the geometric field. And these are PECD, which relies on chiral density, and time-dependent PECD, which relies on chiral current. Third class of observables are chiral observables that rely on multipolar expansion of the vector field B, which means that you now consider three components of the field, radial components and two tangential components, and each of these components are scalars, and as any scalar field, you can decompose it into spherical harmonic basis. So each of these global invariants is respective spherical harmonic number, tensorial number, for two longitudinal component and one radial for transversal and one radial component of the field. The multipolar PECD, which has been already observed and numerically and experimentally in works of Demechin, Baumert, and Rosen et al. Weizmann-Bardot group, but the rest of them have not been observed yet, but they should in principle exist. So as a conclusion to this part of my talk, I have told you about new enantiosensitive observables of class 1, which are messengers of charge-directed photoreactivity in chiral molecules. X-rays generate such selective core excitation, and this may allow one to control direction of excited currents, maybe more precisely, oriented molecular ion along desired direction. And required setup for this is linear pump and circular probe. So what is beautiful is really dynamics controls the direction of the geometrical field, because this direction depends on the orbitals that you excite. And by controlling the direction of this geometrical field, you control your vectorial enantiosensitive observables. And one of them orientation CD. The other still have to be uncovered. The geometric field underlies all enantiosensitive observables in photoionization and enables new phenomena. In this sense, new interesting questions and directions are the connection between topology of geometric field in photoionization and topological properties of molecular states and quantized chiral observables. Well, now I will move to synthetic chiral light, and I will tell you about chiral Young double slit experiment. So what is chiral Young double slit experiment? Suppose we have two chiral emitters with opposite handedness. What does it mean that we have two chiral emitters? It means that emitted field has two components in each emitter. There is a chiral component of the emitted field, which is out of phase in two emitters. This is by definition. And there is a chiral component of the emitted field, and it's exactly the same in two emitters. And here you see pictorially these two emitters and these two components. Phi is the relative phase between achiral and chiral emissions from one emitter. Now, as you can see, enantiosensitive emission is odd in x, and on this axis is just the spatial coordinate which connects two emitters, and achiral emission is even in x. It means that the interference of these two these two emissions, even and odd, breaks parity, and we should observe enantiosensitive light bending. So the signal will go in a specific direction, this one or that one, left or right, depending on the sequence of emitters. So this bending will distinguish left-right versus right-left sequence. What is interesting is that although this enantiosensitive light bending happens in the media which are racemic. I could see the question from Pascal, and I don't know, it's up to Fernanda if the question should be asked after or should be asked immediately.
As you want. If it is related to this, yes, please.
Pascal, if it's urgent, I'm happy to answer the question.
Yeah, go ahead, Olga.
Okay, so I go ahead. So the underlying phenomenon which allows you to understand what is going on in this case is polarization of chirality. So I will stress it once again that the enantiosensitive light bending happens in racemic medium, in which we have equal amount of left and right chiral emitters. Now, to understand this phenomenon, let me make analogy between distribution of handedness and distribution of charge. So on the left picture, you see the simple cartoon of charged media, which all consist of positive charges. The next is the sequence of charges which represent neutral media. And finally is the sequence of units which represents charge polarized media. And what happens between this and this, the difference is that we shifted charges with respect to each other, and we created dipoles. The same can happen with chiral media. So this is a chiral media. It contains a chain of right units. This is achiral racemic media, which is a sequence of left-right units, otherwise equivalent and equally spaced. But if we shift left and right units towards each other, we get a chirality polarized medium, and we have introduced chiral dipoles. Now, chirality polarized chain of emitters is simply multi-slit version of the chiral double slit setup. And the question you may want to ask is how to create chirality polarized emitters. And I would answer that one can use chirality polarized light. And you could answer now, what is chirality polarized light? And I will answer that chirality polarized light is locally chiral light with structured handedness. And you can ask, what is locally chiral light? And I can show you my movies. So what you see in this picture is standard circularly polarized light, which we know is chiral. And we know that it's chiral because the electric field vector draws helix as light propagates in space. But the chirality of this light is non-local, in a sense that if we make a dipole approximation, which means that we consider our field, how it changes locally in every point in space, then you see that light is not chiral, and the electric field vector simply traces circle in space. So what we wanted to create light, which is, oops, sorry. We wanted to create light which is chiral already locally, which is chiral in the electric dipole approximation. And in this light, the electric field vector, this red vector, traces chiral structure, for example, helix, in time, in one period of field evolution. And what is important that this red vector starts from the same point in space. And it can trace not only helix, any chiral three-dimensional structure, any chiral Lissajous figure you can come up with. And the nice property of this field that it's chiral already in the electric dipole approximation. Its headness basically defined by its structure in time, and it creates an Enantio-sensitive optical response already in the dipole approximation and can be controlled fully by the controlling temporal structure of light. And this field can be created. This field doesn't have to have a helical form, doesn't have to draw helix. It can draw a different chiral structure. And a particular realization we come up with is what you see in this picture. So the light that you see here consists of two colors, the elliptical omega field polarized in XY plane and two omega field linearly polarized along Z-axis. And it draws a chiral structure in time, and you see this structure, and the headness of this pulse is controlled by the relative phase delay between these two colors. Now, what you see here is a setup which can be used for generating such light. It requires non-collinear setup in which you have two beams with propagation vectors K1 and K2 under small opening angle. In our calculations, it would be 10 degrees. And in each beam, you have the linearly polarized pulse in the propagation plane, omega pulse, and linearly polarized 2 omega pulse, which is orthogonal to this plane. So, and this happens in each beam, and the phase delay between omega and 2 omega in these two beams, they control the structure, temporal structure of the pulse. And this light can be used to create field which is globally chiral in the entire space, or you can structure headness in space. And in particular, you can create headness which behave exactly like we would like to for the chirality polarized case. So the headness of light that you can create playing with the relative phases is shown here. So effectively, we created chirality dipoles because we have now headness which changes this way across the transversal coordinate. And this transversal coordinate I'm showing, it's this coordinate. Now, it means that we can realize chiral Young double slit setup and show it in one of our favorite observables as high harmonic generation. So what you see is harmonic 12, and this is a typical parameters that we used in our simulation on propylene oxide. And what you see is an anti-sensitive light bending of harmonic 12, which is generated It bends to the right if it is generated in right molecular enantiomers, and it bends to the left if it's generated in left molecular enantiomers. And the quality with which this happens can also be called a circular dichroism, is very high. It can approach 200%. So that's my last slide. And what I have done in the second part, I introduced the concept of polarization of chirality and new observables taking advantage of distribution of Hednanness in space. I introduced light with structured Hednanness, which is chirality polarized light, and Chiral-Young's multi-slit setup and its realization. And finally, Enantio-sensitive light bending as an ultrafast chiral probe. Thank you very much for your attention. I'm ready for questions.
Thank you very much, Olga, for this beautiful talk. So I remind the audience that they can ask questions through this Q&A link that you have in the application on the right-hand side. Okay, so I know that this takes time to write the questions, so I don't see any question yet. So maybe I should start to give some time to the audience to ask the questions. I mean,
Nanda, if you don't mind, if we have a few seconds, I forgot one of my slides actually.
Oh, yes.
No, it's just purely, I would like to show it.
Yes.
I was showing the, thanks to my to my co-authors, but I skipped again, strange. Okay, sorry, that's going to be quick. Just wanted to also thank my colleagues with whom I discussed a lot chirality, and this is Bordeaux team, Valérie, Bernard, Jan, Sam, and others. This is Paris team, Laurent and Gustavo. This is Kassel team, Philippe and Thomas. And I also would like to draw attention to their papers on similar things. Thank you. Now it's proper.
Okay, that's a very important slide, of course. You should not miss it. Okay, I don't see questions yet, at least in my screen. So I have, well, first of all, a comment which I think is really impressive. The degree of control you can achieve to shape, you know, the your light by giving it chirality the way you want. That is impressive. And also you have, you know, time resolution. So I have a very fundamental question. You know, chirality is something that the molecules have, but at some point, you know, when the molecule is built or is formed, it decides to take one chirality or the other. And in fact, in nature, sometimes there is an enantiomer that prevails and the other one is not seen. So I was wondering if, what is your opinion? If by using some of the strategies that you have mentioned, you could access in real time the early stages in which the molecule is formed and decides to take a given chirality or the other.
So basically you are speaking about something like antisymmetric synthesis, right? And yeah. So basically, well, first of all, this is a very fundamental topic, which is called homochirality of the universe. That is what Fernanda referred to as a prevalence of one enantiomer in biological organisms versus another. And as far as I know, this remains as an unsolved question, although a lot of people research in this direction, chemists, biologists, also physicists. For example, I know that Laurent Nahon is doing very interesting experiments related to astrophysics. What I wanted to say is my personal perspective. I personally think that chirality is a ability of nature record a bit of information in biological systems, such as yes or no. So in this sense, in my view, it is only wise to have preferred chirality so that this information is transferred in a proper way. And in principle, the way how I would approach it is really this, maybe it sounds like a physicist way. So basically, biological species, they exist for relatively high temperatures. I mean, normal temperatures. They are not in vacuum. Other way of creating informational storages probably do not exist because they are also randomly oriented, and chirality is rotationally invariant. So this, I think, may be a reason regarding the various, there is really a lot of literature on this stuff related to various reasons why that could happen, from parity violation to prevalence of circularly polarized radiation in the galactics. But I really not, I wouldn't be able to tell you a lot about it.
But it's as you say, it's a very fundamental problem and unsolved problem. And I was wondering if, attosecond science could provide an additional tool to look at these things, maybe.
Yeah, I guess that would mean that one could try to resolve in time some anti-symmetric synthesis reaction and basically provide picture which addresses electromagnetic forces and not the quantities of thermodynamic nature, which are usually considered in the catalysis. So that could be one of the routes.
Okay, I'm checking. I don't see questions yet. I don't know if I am looking at the wrong place, but
there are no current questions for now.
Okay, thanks, Rob. Okay, so well, let me ask a second question. Again, it's curiosity. So you had proposed different observables that show up chirality in a more efficient or way than, let's say, photoelectron circular dichroism, which is something that has been widely used for many years. You are proposing other possibilities to observe this chirality. How easy they are to be implemented experimentally? Because photoelectron circular dichroism is rather straightforward to implement experimentally, but I guess some of the techniques you have mentioned or ideas you have mentioned may be difficult experimentally. Could you comment on this?
First of all, the idea of, first of all, I would like to say that I wouldn't say that our observables are significantly more efficient than PECD, because PECD can reach 80% of the signal, so I think it's pretty efficient. I would just say that they are on par with PECD. Now, regarding synthetic chiral light, I know about experiments that have already realized it. So it's, as far as I understand, it's a pain, but this is doable. Regarding the setup that I presented today, linear purpose circular probe optically on chiral molecules was realized in Bordeaux group in the experiment, I think was led by Valérie Blanchet, and I think Combi is the first author. And the difference is only in the detection, is that one needs to detect the fragments and they angle resolve the fragments. I think that should be also possible. And I think this kind of experiments, not maybe in chiral molecules, but definitely have been done before. So I would not, as a theorist, I would not consider this as something super challenging, but of course, every experiment is challenging.
Maybe some of the experimentalists attending the seminar could complement the answer if they want. Anyway, I don't see questions, so I don't know. Maybe we could close. I have many other comments and questions to ask, but I think it's we can do it in private. Not all of them related to science, by the way. But okay, so since I don't see any questions, I think we can close the session. I want to thank Olga once again for giving this very, very nice seminar in this hot topic, but at the same time very complicated topic, which is chirality, that many of us have problems to understand in full. And I think her presentation has helped us a lot to understand the basic principles of this. So thank you, Olga. And I think with this, we can close. Thank you.
Thank
Goodbye.
you. Bye.